this is Jack Jackson back again. Let's look at another related rate problem. A highway patrol officer is parked behind a billboard, and the billboard is 200 feet from a long straight stretch of interstate, say I-40. And down the highway, about 270 feet from the point on the highway closest to the officer, is an emergency call box. The officer points the radar gun at the call box and measures the speed of the traffic passing the box. Actually, the radar unit actually measures how fast the distance between the radar unit and the traffic is increasing at the time the automobile passes that box. If the posted speed limit is 75 miles per hour, what is the maximum speed measured by the radar gun which would correspond to a legal speed of the traffic? Okay, so see if you can work this one out and come back when you have your answer and check it. Press pause now. Well, notice this time we're going to need to draw a picture. Okay, so here's basically the picture. Here's this long straight stretch of I-40. Here's the police officer standing right here. There's a billboard right in here somewhere. Okay, maybe over here on this side of him. And the traffic goes by, say, going to the right here. Right here is where the box is, and so this is where the traffic is right when he pings it with the radar gun. Now, actually, this point closest to him is on the interstate is right here, at the corner of this, where this right angle is. Of course, the closest distance is going to be a perpendicular distance, so that's a right angle. And that distance is 200 feet. And this distance the car is from that point is x feet. And of course, x is going to be increasing as time goes along here. And it's going to, right at the point we're going to be interested, x is 270, but x is actually a variable because it's changing. And the distance from the radar gun to the car is this distance r, which is also changing. So if you think of this dynamically, as this point moves further and further out here, this both x and r increases. Time increases, but the 200 is fixed. Okay? Well, what relationship do you have here? Well, we have a right triangle, and of course, probably the most famous theorem in geometry, one of them certainly, is the Pythagorean Theorem, and so we can apply that here since it is a right triangle. So we know r squared equals x squared plus 200 squared. Now we can differentiate both sides with respect to time. So we used our picture right here to help us set up our relationship, and we had to use a fact from geometry, the Pythagorean Theorem, to help us with that. So now we have a relationship between r and x. Now we differentiate both sides with respect to time. And of course here we get 2r dr over dt, and over here we do 2x dx over dt plus 0. So we're doing implicit differentiation here. Now divide both sides by 2r, and the 2's cancel, and so we get dr over dt is x over r times dx over dt. Now at the point we make the measurement, the car is right here, and we can substitute in the r and the x that we have at that point. So we know that x is actually 270 feet at that point. What is r? Well, let's see. When x is 270, r is 270 squared plus 200 squared, square root. That's the square root of 112,900, or 10 times the square root of 1,129. Okay, and we'll round off things at the end here. But we can plug these numbers in at this point. Now notice we know, which one do we know? We know the speed limit. Now the speed limit is actually the maximum speed that the car can go down the road, which is really dx over dt. But what the radar gun is measuring is not dx over t, but rather dr over dt. And so we can we know dx over dt, and we want to solve for dr over dt. dx over dt is 75 miles per hour. X is 270 feet. R is 10 times the square root of 1129 feet. And we potentially have a problem because we have miles here and we have feet, but actually we don't because the feet cancel out and we get miles per hour, which is probably what we want anyway. So here's what we get as an exact value. Approximate that because real world problem, we want an approximation. Of course, all these digits are probably not accurate. So let's say we go to 1 decimal place. That's about 60.3 miles per hour. So the car is going down the road really at the radar gun, when it reads 60.3 miles per hour, the car is really going 75 miles per hour. So if you get pulled over for a traffic ticket, probably don't want to explain this to the policeman. Now this is an extreme example because the policeman is not really going to be 200 feet from the road. He's just going to be almost right on the road, just barely off of it. But even then, the case is true that the actual speed is going to be a little faster than what the police car is actually measuring with the radar gun. So the only way to get it accurate is if the police car is stationary and is right behind the car that's moving down the road. Then there would be no difference in the two measurements. So kind of interesting. So that gives you an example of where you can draw something, use some geometry to come up with a relationship, take the derivative of both sides with respect to t, plug in your numbers at that point after you've done the derivatives, then plug in your numbers, and then we've got that. Now, maybe in a later video, next video here, we might do a couple more, but let me go ahead and throw out a couple of problems here, maybe 3 problems here for you to work on your own. You might write these down, work on them, and then come back to see some solutions at some point when I get this posted back up. So here's a problem, problem 79. A baseball diamond is a square that's 90 feet on a side. Suppose a batter hits a ball along the third baseline, and let's say the ball is traveling at 100 feet per second. And he can run, let's suppose he can run to first base at 25 feet per second. Okay? At what rate is the distance between the ball and first base changing when the ball is halfway to third base? Okay, that's the first question. Second question, at what rate is the distance between the ball and the player changing when the ball is halfway to third base? And then, suppose the third baseman catches the ball on one hop at third base. Let's make it more realistic. It takes him, what is it? Maybe half a second. To catch and then throw the ball. How fast does he have to throw the ball in order to get it to first base before the runner gets there and make the out? Okay. All right, so that's an interesting problem. Next one, a railroad bridge is 20 feet above and at right angles to a river. A person in a train is traveling at 60 miles per hour, passes over the center of the bridge. At the same time, a person in a motorboat traveling 20 miles per hour passes under the center of the bridge. How fast are the two people separating, say 10 seconds later? Okay, that's going to require you to draw a three-dimensional picture. So think about that a little bit. And question number 81, a highway patrol plane flies 1 mile above a straight section of, say, rural interstate highway at a steady ground speed of 120 miles per hour. The pilot sees an oncoming car with radar, determines that the line of sight distance from the plane to the car is 1.5 miles and that the distance is increasing at a rate of 136 miles per hour. Should the driver of the car be given a ticket for speeding? Explain it to the judge. And if you're in Arkansas, where I'm making this, and you're on a rural interstate highway, okay, then we know the speed limit is 75 miles per hour. So let's just throw that in there because you're going to need the speed limit, and it changes depending on which state you're in. So let's say speed limit is 75 miles per hour. Okay, and then explain it to the judge, or explain your reasoning. In all these cases, you want to be able to explain what you're doing. So see if you can work out those 3 problems on your own, and come back in the next video and we'll look at the solutions.